Experiment 6 is about kinetics of solvolysis of third butyl chloride. Objectives of the experiment are to determine the effect of solvent polarity and temperature on the reaction rate. From that, we are going to calculate the activation energy and collision factor based on Arrhenius equation. To achieve the objectives of the experiment, we are going to measure the reaction rate constant at 3 different solvent polarities. Measure the reaction rate constant at 4 different temperatures. And from this, we are going to determine the energy of activation EA and the collision factor A, or the number of collisions per second. So first, I'm going to, I have the reagents in here, and I am going to follow the procedure. Technically, we are going to have 4 different water baths during the semester, but I'm only going to show you 1 water bath, and then I will show you the other water bath. But first of all, we are going to follow the table. In this table, the first column has the solvent mixture, and then the volume of the water, and then volume of sodium hydroxide, and volume of third butyl chloride in acetone. So I have the sodium hydroxide, which is 0.01 molar concentration, and then water is just RO water, and I have 3 flasks. So I labeled the 3 flasks as 60% water, 40% acetone, 70% water, 30% acetone, 80% water, 20% acetone. So I have here 3 flasks. That's 60% water, 40% acetone, and then 70% water, 30% acetone, and then 80% water, 20% acetone. So I'm going to use the straight pipette. Okay, so this is for water because we need the highest volume is 6 mils. I'm going to use a 10 mil pipette, straight pipette. And then for the sodium hydroxide, another straight pipette. Okay, but because the maximum volume is 4, I'm going to use a 5 mil pipette. So that's the maximum. So this is the straight pipette that I showed you earlier. So it's a straight pipette, and notice that it's not to deliver, meaning that at the bottom the scale is 10. So make sure that you're measuring it only up to here. Don't deliver up to the bottom, up to the end. Okay, so that's one of the things that you have to be careful when you're using a straight pipette, because it's not to deliver. So now I'm going to measure 2 mils. So I have here 2 mils water. Right, so I'm doing 60% water, 40% acetone. So I'm going to put 2 mils water and then 4 mils of sodium hydroxide. Take note that the total volume is 10. So that's why the percentage of water, because this is aqueous, percentage of water is 6 and total is 10. So that's why it's 60% water and 40% acetone. The third butyl chloride is in acetone. So I'm going to do 2 mils. So some of you probably have done this before, how to pipette. I'm going to use a bulb. Okay, so I'm going to dip it all the way to the bottom. So I can also do for the others. Okay. So this one I have 2 ml water, 4 and 6. So I'm following this. 2, 4, 6. 60%, 70%, 80%. So 2, 4, 6 ml water. So I press the bulb, and then I put it on top and then let it go up. So I'm gonna let it go up to 0, the water. Okay, and then I'm holding it with my left hand. So release, and then I want it on 0. The lower meniscus sitting on 0. Then I'm gonna put 2. Stop. And I'm gonna put here 4, so I'm gonna end at 1, 2, 3, 4, so on 6. Okay, so I'm gonna cap this, cork it, and then I'm gonna withdraw up to 0, so I have to deliver 6 on the last one. So you have to do it several times, and then 0 again, and then 6. So I have to stop at 6. All right, so those are my samples. So if you're doing this in the lab, you are going to do it 2 or 3 runs each. So I'm doing just one. So typically you're going to have another flask with 60%, 70%, and 80%, because you should have 2 runs. So I'm going to put it here just in case I need to redo the water. So this is for the water. Okay, so these are my samples, just my water. And then I'm now going to add sodium hydroxide. So sodium hydroxide in the first one, I'm going to add 4. Second one, I add 3. Second one, I add 2. So the first one, I'm going to add 4 ml of sodium hydroxide. This time, I'm using this pipette. Okay, so I'm going to, because this one is up to, this is up to 5. So I'm gonna go up to 0, and then I deliver up to 4 ml. Okay, so do the same thing. Use the bulb, and then I'm going to withdraw until 0, and I need to add 4 ml on the first one. So I need until 4 ml. Okay, so now I cork it. It's the first sample. The second one, I need 3 ml. So 3 ml, I can also withdraw just up to 2, and then to 5, then I have 3 ml. So I'm going to deliver until 5 ml, because I need 3. Okay, so that's the second sample. The last one, I need 2 ml. So I can just go up to 3. 3. Okay. And then deliver to 5. So that gives me 2 mils. Okay? So that's my third sample. So I can cork this, and then I will put it here just in case I need to reduce. In reality, you need one more set of the 60, 70, and 80. So the next step is I'm going to now equilibrate the solution. So this is the water bath, and the temperature right now is 30. So you can see that the temperature is 30 degrees. And then you can also read it here. So I have a thermometer, and that's about 30 also. Okay, so you can set it here. So it's electronic. It's 30 degrees. So the water bath should be 30. So I just put the solution, the 60% water, 40% acetone. And so I want to equilibrate this for a few minutes. And then the third butyl chloride in acetone is already equilibrating. So let's wait for that to equilibrate before I mix. So I have it equilibrating for more than 10 minutes. I'm ready to mix it. So this is the indicator, bromophenol blue indicator. So I'm going to put a drop in the solution of water and sodium hydroxide. So a drop of the solution. Okay. So I'm going to take it out. Oops. Just to show you that it's blue. Okay, so the indicator is blue in basic solution. So remember we only mixed sodium hydroxide and water. And I put 1 drop of bromophenol blue indicator. So I'm gonna put it back into the water bath. So I'm going to clamp it back. Okay. Okay. Remember we're doing the 60%, the first row in here. So the mixture was 2 ml water and 4 ml of sodium hydroxide. And I'm now going to add 4 ml of the third butyl chloride in acetone, which is the solution at the back, this one. And that's also equilibrating together with the solution mixture of the base and water. So I'm going to use a straight pipette. So the same straight pipette, so we are going to, I'm gonna pipette up to 1 and then deliver up to 5, okay? But I'm also going to time it when I delivered already like 2 ml, okay? So this is again our stopwatch. So I'm gonna turn it on, okay? Reset, and then I'm going to press start when I'm ready, when I delivered 2 ml of the third butyl chloride solution into the base solution. So I take out the cork, and I will take this out, okay? And then I'm going to now pipette. So I want it at 1 ml, okay? 1 ml. 1 ml mark. And then I'm going to add here up to 2, up to 3. 0, 1, 2, 3. So I'm delivering 2 mils. So remember, I need 4, right? So now, so half of the volume, and then I press start, and then I'm going to deliver up to 5. Okay, cork it again, and then on this one I'm going to take out because I need to swirl it. Okay, and then I cork it, and I'm gonna swirl it. So basically it's like titration. So I'm going to swirl it until I see a change in color, which is greenish. So that changed in color already. That's like 52 seconds. So that was fast. Then it will continue until it's like changed into yellowish. Okay, so it changed color about 52 seconds. So that's the end point of it. Okay, so I actually illustrated. If you have a colored in the handout, you will see the transition. So start is blue, the end point is light yellow, it will turn eventually to yellowish green. Okay, so that's the first data, and typically you will run another sample, so we take the average. So I'm going to do the next sample, which is 70% water, 30% acetone. So I'm now doing the 70% water, 30% acetone, and then I'm going to add the third butyl chloride. And then I'm going to add 1 drop again of the bromophenol blue indicator in this basic solution. So just 1 drop. So again, blue. Start with blue. So in base, it's again blue. And I'm gonna clamp it again. Okay. So I will take that out. I will take this out. And I'm now going to pipette third butyl chloride. So remember, we're here, the second row. So I'm pipetting 3 mL of the third butyl chloride. So once I added half of it, I'm gonna start timing. So again, straight pipette. And then I'm gonna pipette up to 2 mL. So that's 2. Okay. All right. So now, once I deliver about 1.5 ml, I'm going to start timing. So up to about 3.5. Okay. And then I'm going to take this out, and then I will swirl it. Okay, so actually it already happened. It already changed color, 26 seconds. It's really fast. Okay? So, all right. So that's done here. All right. And then I'm going to take this out. So I'm going to equilibrate the last sample over here, 80%. I'm going to clamp it here, equilibrate it for 10 minutes. So when you're doing it as a group, so typically I divide the class into 4 groups, meaning that we have 4 different water baths, and you can do it simultaneously. So like 4 or 5 or 6 people in a group, then you can do 2 runs each time. And you can also divide the task because you're going to be doing 2 samples for each run. So you're going to be repeating what I did maybe 1 more time or 2 more times depending on the data, because the 2 data should be close to each other. If it's too far, then you have to repeat it. So right now I'm done with this part here. So we're gonna do the last one, which is 80% water, 20% acetone. So I'm gonna wait for 10 minutes for it to equilibrate. So temperature is still 30 degrees C, and then the thermometer reading is still 30. Okay, so I'm now doing the last part, which is the 80% water, 20% acetone. We combine 6 water, 2 sodium hydroxide, and I'm now going to add 2 mL of the tert-butyl chloride. So again, after I add 1 ml, I'm going to start timing and then swirl it. Okay, so as a note, I'm using a slightly different pipette. So this pipette is to deliver. So as you can see, compared to the previous pipette, so if I pipette 2 mL, I can go up to 3, and then I deliver up to the tip 2 mL. Okay, so I'm going to use this one. Okay, so now I'm going to take that out, and then I'm also going to add again the bromophenol blue indicator, 1 drop. So let me take it out to show you the color. Submerged in the water, it's hard to see the color. So again, it's blue, purple. Okay, and then I have it here, put it back into the water bath. Okay, and now I'm going to pipette 2 mL of the tert-butyl chloride and then start timing. So the same thing, I'm going to press the bulb. So we just need 2 mL. Okay, so 2, so I have 3, and then I'm going to deliver here about 1 ml to 4, and I'm gonna start the time. Okay, and then I will take this out and start to swirl it, and actually it already changed color. 11 seconds. Okay, so 11 seconds, done. Okay, so 11 seconds was the time for the 80% water, 20% acetone. So again, it changed color at 11 seconds for the 80% water, 20% acetone. Right? So after this, it's basically clean up. However, as I mentioned, that typically we will have 2 runs. So I showed you an example on how to do it, and then I will give the data for the rest of the class. Typically we share the data, the class shares the data. So for example, another group will be doing 25 degrees C. So it's going to be in this portion of the water bath. So this is higher temperature. This is now lower temperature. So another group will be doing this portion because we want 4 different temperatures So for our purposes, for the class, I will give the data, and then you will now answer the questions for the lab report. So typically, for the whole class, we will fill this up. So for now, I did 30 degrees C, and then I have one data point for these, but I'm gonna be doing one more run, one more trial. So I will take the average, and that's what you're gonna see here. So the table is gonna be like this. So I will give the class the data, but I will have 4 different temperatures, and I will fill up this table. So I will have 4 different times in here in seconds. So 4 different times the average of each of the runs. Okay, so 4 different times, 4 different times, 4 different times, and 4 different temperatures. So we're done for this experiment, and that's basically it. And we are now going to answer the questions in the lab report. The following slides will show the calculations for the experiment. Reaction rate equation. The rate is equal to the disappearance of third butyl chloride over time, or the change in third butyl chloride concentration at time t over the change in time is equal to the rate constant K times the concentration of third butyl chloride at time t. Rearranging this equation gives you this equation. Putting this concentration of third butyl chloride in the denominator and putting dt, or change in time, on the right side gives you this equation. Upon integration of this equation gives you minus ln of third butyl chloride concentration at time t over the initial concentration of third butyl chloride gives you rate constant K times change in time. Reaction rate constant derivation. In this experiment, we are measuring the effect of solvent polarity and temperature on the reaction rate. We are not measuring the effect of concentration on the reaction rate. To be able to measure the effect of solvent polarity and temperature on the reaction rate, we are going to fix the concentration. To fix the concentration, we are going to define some parameters. The concentration of third butyl chloride at time t is equal to the concentration of third butyl chloride when 10% of it has reacted. This equation was shown in the previous slide. We are now going to substitute the numerator, which is the concentration of third butyl chloride at time t, with a specific concentration, which is the concentration of third butyl chloride when 10% of it has reacted. This expression now becomes the expression below. So minus ln of the third butyl chloride concentration at 10% reaction over the initial concentration of third butyl chloride is equal to the reaction rate constant K times the time at 10% reaction. This expression is now more specific than the expression above. How do we know that the 10% of third butyl chloride has reacted? This equation is the reaction in the experiment. Third butyl chloride reacts with water, forming third butanol and hydrochloric acid. One equivalent of third butyl chloride reacts with one equivalent of water, forming one equivalent of third butanol and one equivalent of hydrochloric acid. The reaction is SN1 mechanism, favored by a tertiary alkyl halide and by a weak nucleophile water, which is also the solvent. This mixture in the experiment is colorless. How do we know that the products are formed? We know by adding the indicator at the beginning, which is bromophenol blue, and the color is blue in basic solution. The base we added at the beginning was sodium hydroxide in water with a concentration of 0.01 molar, which is 10% of the initial concentration of third butyl chloride, which is 0.1 molar. So we started with third butyl chloride concentration of 0.1 molar. It will now react with water, forming the products. So when 0.01 molar of the third butyl chloride, which is 10% of the initial, is converted to hydrochloric acid, which is now 0.01 molar, 1:1 equivalent, so 0.01 molar producing 0.01 molar, which is equal in concentration as the base. It will now neutralize the acids. It's an acid-base reaction. The amount that we added of the base at the beginning is fixed. It will not change. However, the hydrochloric acid that is being produced will change until all of the 0.1 molar is converted to the products. So, the end point is indicated by the change in color of the bromophenol blue from blue to light green. So when 0.01 molar of hydrochloric acid is formed from 0.1 molar of the third butyl chloride, the base is now neutralizing the acid. That is the end point. So this is like a titration. The color of the indicator changes when the end point is achieved. So now we know that 10% of the third butyl chloride is reacted when the indicator changes color. So after neutralization, the reaction is still happening. It will still continue because you still have 90% of the third butyl chloride that is left. So initial concentration of the third butyl chloride is 0.1 molar. That is the same as this value in here. So after 10% reaction, the concentration of third butyl chloride after 10% reaction, or what is left behind, is going to be equal to the initial concentration minus 10% of the initial, and now it's equal to 90% of the initial, or 100% minus 10% is equal to 90% of the initial, or 0.9 of the initial concentration of third butyl chloride. So this value, which is the numerator in this equation above, is now going to be equal to 0.9 of the initial. So going back to this equation, we can substitute the numerator with this value. So in this expression, after substitution of the numerator, will now become this expression below. So minus ln of 0.9 times the initial concentration of third butyl chloride, which is the same as this value, which we substituted in the numerator, the same now as this numerator. So in the numerator, we have initial concentration of third butyl chloride, the same as the denominator, initial concentration of third butyl chloride. We can now cancel the initial concentration above, initial concentration below. What is left behind is minus ln of 0.9. Minus ln of 0.9 becomes 0.1053, is now equal to the reaction rate constant times the time at 10% reaction. This time at 10% reaction is the observed time in the experiment illustrated. So there are 3 times at 60% water, 70% water, 80% water. So this time at 10% reaction is the observed or the experimental time in the experiment. We can now calculate K, which is equal to 0.1053 over the time observed. So K is equal to 0.1053 over the time from the experiment. In the experiment, we have 3 different times corresponding to 3 different solvent polarities. Because we will have 4 different temperatures of water baths, we can now determine or measure the effect of solvent polarity and the temperature on the reaction rate. Data calculation. The table on the left is going to be the format that will be provided for each student via email. This is going to be an Excel format. So we will have 4 different temperatures, including the temperature of the water bath illustrated in the experiment. So this corresponds to different water baths. We will have 21 degrees C, 23, 26, and 30. This will be the same, but this can change. So this will be filled up. So for 60% water, you will have 3 more times corresponding to 3 more temperatures. The same thing for 70%, you will have 3 more data points. And then 80%, the same thing. 3 more data points corresponding to 3 different temperatures. So calculations and graphing can be done in Excel. So you can just expand on this template. So make a column, because the first step is you are going to convert the temperature in degrees C into Kelvin, and then convert that Kelvin into 1 over T or 1 over K. The unit now is per Kelvin or K to the minus 1. So for example, in this case, after converting degrees C into 1 over K, this number will be small. So you will have 4 different points or 4 different data because you have 4 different temperatures. That becomes the x-axis. Next step is to convert the time observed in the experiment in seconds into rate constant K, which is equal to 0.1053 over time for each solvent polarity, 60%, 70%, and 80%. For example, the K for this time is going to be equal to 0.1053 over 52 seconds. That K is going to be converted into ln K. You are going to do the same thing for the other times in here. Convert that into ln K. So you will have one set of ln K corresponding to 60%. So put 60% above. And then you are going to do the same thing for the 70%. Make another column corresponding to ln K for the 70%. The third one, 80%, another set of ln Ks. Therefore, you will have 3 columns of ln Ks corresponding to 60%, 70%, and 80%. Those 3 ln Ks will become the y-axis. There will be 3 lines in one graph, each line for each solvent system. ln K, small k as y-axis, 1 over K, capital K as x-axis. There is only one set of temperature, but you will have 3 sets of ln Ks corresponding to each different solvent system. In Excel, there is a tool called trend line. You use this to get the equation of the straight line. You will need this for the next information in the next slide. So the slope in the y-intercept can be determined from the trend line or from the equation of the straight line. Arrhenius equation is the expression of the dependence of the rate constant K with temperature in Kelvin. K is equal to A, the collision frequency or the number of collisions per second or per second, times E raised to EA over RT. EA is the activation energy. It is the measure of how fast the reaction goes. R is the gas constant, which is equal to 8.314 joules per Kelvin per mole, or 1.99 times 10 to the minus 3 kilocalories per Kelvin per mole. Temperature is in Kelvin. The higher the temperature, the reaction is going to be faster. This equation, if you take ln K, is going to be equal to the exponent EA over R times 1 over T plus ln A. If you plot ln K in the y-axis versus 1 over T or 1 over K in the x-axis, So y versus x, ln k versus 1 over t, you will get a straight line coming from the trend line in Excel. So the straight line, or equation of the straight line, will give you the slope and the y-intercept. The slope is going to be equal to EA over R. To get EA, you multiply the slope times the R. The R can either be 8.314 joules per Kelvin per mole or 1.99 times 10 to the minus 3 kilocalories per Kelvin per mole. If you're using this, the unit of your EA is going to be joules per mole. If you're using 1.99 times 10 to the minus 3 kilocalories per Kelvin per mole, the unit of the EA is going to be kilocalories per mole. To get the y-intercept from the equation, it's going to be B, and that's going to be equal to ln A. To get A, which is the collision frequency, you get it from the y-intercept. So A is going to be equal to inverse ln B. So again, it's going to be inverse ln B. In the experiment, you will have 3 lines. Therefore, you will have 3 equations of a line because you will have 3 solvent polarities, 60%, 70%, and 80%. Therefore, you will have 3 values of EA and 3 values of A in the experiment.